good to be back. I know it's been a little while, but I've had quite a lot on. It's a miserable day here in the UK, so I thought let's come down the shed and let's make another video. What I'm going to be talking about today is changing capacitors, and we'll have a look at resistors as well in an old radio. I've got my old DAC10 here, which you'll have seen in an earlier video. It's never been very good, to be honest. Its signal strength is a bit weak. You tend to get a lot of hum. So I think the time has come to go through it and have a look at capacitors. So what I'll be doing is, I'll be telling you what I'll be doing. We'll have a little talk about dielectrics of capacitors, which are the right ones to use. Should you replace them all? Which ones to replace? Should you be testing them? That kind of thing. I don't know how well you're going to be able to see this, but this radio is full of these waxy type capacitors here. They're almost kind of sticky to touch. So the question is, do you test them or do you replace them? And the answer is no, you don't test them, you replace them. They are known to be very unreliable capacitors. They're a kind of waxy paper dielectric, and they just don't last. So there is no point in testing those, you replace them. So, the question is, what are we going to replace them with? In terms of dielectric, you really don't have to worry too much. I mean, the best type of capacitors you can get are polypropylene, only from a current handling really, but that's really not applicable in this case. There are a couple of areas which I might point out later where maybe we want a slightly better capacitor, but in terms of dielectric, you really don't have to worry. So you've got polyester, you've got ceramic, you've got disc ceramic. You know, they're very cheap. The only thing you've got to watch with disc ceramic is the voltage rating, and sometimes from the circuit it's not quite clear what kind of voltage you need, and often on these little disc ceramics it's not actually written on it what it is, so you do need to be a bit careful there. But the rule really is, if you don't really know what voltage capacitor you need, just go for one that's 350 volts or above, and if you do, you'll be safe. You know, if you're coupling an anode to a grid, you know, you can have quite a lot of voltage across it, so that's just one thing to watch. So I'm going to go ahead and we're going to look at these capacitors now, and I've got to start taking it all apart, and we'll gradually replace each one. And I'll take a load of photographs as we go, and you can see what I'm doing. Oh, and the other thing to say before I get started is that when it comes to electrolytics, electrolytics have got a very bad reputation. There's a lot of people who would say electrolytics, just replace them, because if they haven't failed now, they will at some point. And I'm not saying that's wrong, but it's not quite my view. I think electrolytics have got a bit of an unfair reputation as being unreliable. They can go on for a long time and be absolutely fine. So for me, I want to test electrolytics. And I'll be showing you later a little technique for testing them, which I've got a bit of faith in, and it's just stuff you can make yourself very easily, but it gives me a little bit of faith that the electrolytics actually is alright, or it's not alright. Well, getting the waveband selector out was a bit of a challenge, and you'll see that it looks like I've been really vicious. I've just cut the wires. And the reason that I've cut the wires is that the insulation's knackered anyway. I've got to replace it, and if I cut the wires, it's very clear to me where I've actually got to rewire it, and it means now that I can get at all these waxy capacitors. We'll have a look at this. We can give up the switches a very good clean now, and move from there. The waveband selector block here has got 6 capacitors on. Yes, they're wax ones, but I don't think I'm going to change them. The reason is because they are high tolerance ones. So if I look at this one here, for instance, this says 605 puff plus or minus 1%. Well, 605 puff is a very unusual value, so they wouldn't have done that without a reason. And if they're mica, they're not likely to have failed, so it's best not to touch those, I think. Folks, I've been checking some of these resistors as I've been going along, and I'm getting some really high values. It's really not what I expected. You know, you might say 10%, and some of them are silver band, that's 10%. But look what I'm finding. I've got this is a 1 meg resistor. So that is, you know, that's 20% out. there's another 1 meg resistor here. That's getting up, that's 30, it's more than 30% out. There is a 2.2 meg resistor here. Look, you know, that's beyond 3 megs. Let's try another one. There's let's try this 100k here. Sorry, 10k, beg your pardon. Let's see what that is. See, that's 13k. Now at this point, I'm suspecting there's something wrong with my meter. So what I've got, I always keep some high precision resistors just in case this kind of thing happens. And I've got a 1 meg ohm, 0.1% here. And it's 1 meg ohm. So I have got a lot of high value resistors. I know these carbon resistors do get stretched, so I'm going to have to be checking every single one and replace as necessary. You know, you can tolerate 10%, perhaps maybe even a little more, but when you get to about 30%, you think, oh no, something's a bit wrong here. So I'm gradually going to be replacing these waxy capacitors and a lot of resistors at the same time. Well, I think I've done practically everything I want to just in the chassis here, certainly on this bit. It has genuinely surprised me how many of the resistors I've had to replace. Practically all of them. There's a 15k, a slightly bigger 15k here, which I've left in. That's, you know, that's all right. There's a 220 ohm there, that's all right. But the rest of it, you know, they were way out. They were like 30% high. So I've replaced those. There is a big watty 10k resistor here, which is measuring about 11k. Now I could shunt it with something, I guess, but I think I'm going to leave it. I think that's all right. So replaced all these capacitors here. I've put a genuine X2 capacitor here right across the mains. You always want to do that if you can. I've used 1 disc ceramic down here, okay, sort of noting the voltage. So that's about as much as I want to do in there. I want to turn my attention to the electrolytic now. This is a 32 mic and a 16 mic all in one can, 275 volts. And with this one, you know, I could cut off the bottom because it's in its little clip there. I could cut off the bottom, you'd never see it, and I could put some more capacitors inside, but I really don't want to do that unless I have to, so I think it's worth testing this cap. Now first off, you know, let's just see what the meter says. Let's just have a look. It takes my meter a moment or two to come to life, and just give it a second or two. Come on, there you go. Right, so it's saying the 32 mic is 44.7, okay, interesting. And it's saying, just a moment, it's just saying that the 16 mic is 22 mic. Well, that might be right, it might not be right, and actually what its value is, you know, I'm not too worried. Doesn't tell me anything about leakage though, so we need to do something more than that. You can certainly get capacitor testers. But I really want to be able to control the voltage. Well, it occurred to me that if you've got one of these and one of those, which you're most likely to have if you're doing any kind of radio repair, to measure leakage current in an electrolytic, you don't need very much else. what I have set up is a little box here, and the circuit, I'll put the circuit up, you can see it. It's ever so simple. Essentially I'm rectifying the mains, and I'm filtering it, very heavily filtering it, because the mains tend to sort of go up and down quite a lot, so it needs to sort of average it out a little bit. And then I just measure the current through the capacitor. It's as simple as that. I'll explain what this switch and all is about later on, but essentially the switch is on the left hand side, and we're just going to measure the volts across the capacitor with the current going through it. Let's have a go. Here we go. This is one of those times where I prefer one of these old analog meters for this, because you can actually see things happening if something strange goes on. Let's put the meter on milliamps. Okay, wind it up. So I've got the 32 mic cap in here. I'm trying to get a feel for the leakage current, and the volts are going up now, and when I get to about 240 odd volts, I've got about 0.88 of a milliamp at about 250 volts. Make a note of that. Hang on. It's about there, 245 volts, and I've got 0.85 milliamps. Right, let's just wind that down. Yeah, I realised my soldering iron wasn't on. Right, I've got the 16 mic cap connected now, so let's just see what that does. Yeah, the reason it's so slow is because the caps in the box are charging up, but actually I'm already worried, because I'm getting about 2 milliamps, and I haven't quite reached, well, it's about 185 volts. 185 volts, say 2 milliamps. So the leakage in the 16 mic is certainly significantly more than in the 32 mic. Okay. So I guess the question is, what's reasonable? What sort of current do you think we should expect here? Well, I've got a 33 mic 400 volt here, downloaded the data sheet for it, and they actually tell you, or they give you an idea, and they're saying 0.06 CV plus 10 microamps. Let's just give that a go. 0.06 times 32 mic times 245 equals that, plus 10 microamps. So that's 480 microamps on that capacitor, and I'm getting, well, perhaps twice that. Now that by itself, I'd probably say, alright, that's not too bad, but the fact that the 16 mic is more than that, that's a bit of a concern. I was hoping that I wouldn't have to bore this capacitor out, but I'm going to have to. Okay, here's the plan then. So I've got two caps here. That's a 33 mic, it's going in the can. I haven't got a 16, I've got a 22. They're both going to fit in, so I'm going to try and fit those inside this can. I'm going to see if I can cut the end off with my lathe. You can rub it on a piece of emery paper or something if you want to, but I'm going to try and do it on my lathe. Let's see how we get on. Well, there you are, folks. Absolutely perfect job, as you can see. Nothing wrong with that whatsoever. Damn thing slipped out the jaws of the chuck because my chuck jaws aren't quite long enough. How annoying is that? That is absolutely 100% knackered. That's not going to get us anywhere. So in one sense, I suppose it's kind of alright, because the wires that fed this went right through the chassis and they were knackered anyway. But if I put the capacitors on underneath, it means I just get rid of those wires. So in one sense it's a better solution, but my preference would have been to put the capacitors inside that one, but that is no longer an option. Never mind, carry on. Well, a bit annoyed with myself with that capacitor problem. I think if I'd been a bit more careful I could have avoided that, but anyway, I think we're alright. I've got the 22 mic in there. Remember, the 22 mic was my replacement for the 16, and I've got 33 mic in there. I'm kind of conscious that there's a resistor there which is going to dissipate a lot of heat, so I've kind of pushed it away. Also, I don't want to get things too close to the volume controls to induce hum, so I put it there. And also, of course, this has still got to go in, of which it does, so I'm not interfering with that. I think we got away with it, but it would have been better if it was original cap, but there it is. Well, I think what I'll do now is I'll do a bit of work on top of the chassis. Alright, it is pretty disgusting, but I think it's not too bad really. I think all I'll do with that is I'll brush it off first of all, and then I'll get something to clean it with. I know the bulbs are fine, I've previously replaced those. Some of this wiring is rather dodgy, so I'll replace that. I don't think that's going to take too much work. You know, it's a funny thing, because all I was going to do to this radio was change the capacitors. I've done so much more to it. I've changed practically every resistor. There's a couple of resistors I haven't changed. I've changed the mains lead, I've changed chassis wiring, loads of chassis wiring on here which is past it. I put a new grommet in there, all sorts of things. I decided in the end that I would replace this big Watty 10k resistor in here. I'm not sure how well you can see that there. But the one that came out was this thing here. I measured it again, it's not far off 12k to be honest, so I think, well, while I was at it. When you do the calculations on the power dissipation of that resistor, it turns out to be less than a watt. And that is a huge resistor for a watt. But then if you start looking, the airflow is not particularly good here, and the surface temperature can get really quite excessive, which is why they've gone for a big resistor. So in terms of what resistor you want to replace it with, the answer is the biggest 10k I can get hold of that will fit in there, and I've put a 9 watt resistor in, so that should be fine. In terms of cleaning the chassis, I just brushed off what I could to start with, and then I just used a foam cleaner. That's the one I used, and it's still pretty tarnished to be honest, but you know, to get it better than that, you know, the year until then something abrasive, I don't really want to go down that route, because you'll be able to see all the bits that I couldn't get at, and that's absolutely fine. I have tested all the valves and they're all absolutely fine. When I cleaned the chassis, I sprayed some alcohol down the sockets. That's a good thing. And I know that some people like to clean the end of the pins. You know, I've seen people use a wire brush on these. I've never found the need to do that. I'm certainly not saying it's the wrong thing to do, but I found these connections pretty reliable on the end. So all I've done is just brush them. But in terms of testing the valves, I think perhaps I'll just show you how I've been testing one, just so you can see what I've been doing. So the way this thing works is that you have to set the mains voltage, and the assumption is that the mains isn't going to change all the time you're testing it. Well, it might and it might not, so let's just do that first. The mains is pretty stable here. Seems to be a little bit lower in the evenings, and the idea is that you want to get it absolutely spot on that mark, and this thing will change it, and that's pretty close. Alright, there are thumb wheels up here which you have to set the pin connections, which I've already done according to the book, and then it's just a question of setting everything up. Start with everything well, fully anti-clockwise, just reading my book here. So it's saying heater volts is 45. It's saying negative grid volts is 9. Negative grid volts is 9, making sure that I've got that set correctly as well. Anode volts 175. Screen volts 175. It's expecting about 54.5 milliamps. We'll get to that. Just make sure that's on the 100. Yeah, that's fine. And it's saying a GM of 9.5. Well, that's 9, that's 10, that's 9.5. Making sure I'm on the right scale, which I am. Right, off we go. So from there, we just check heater continuity, and that's the heater cold. We just check insulation between the heater and all the other pins. And that's fine. Now that we turn that on, which gives you the valve is hot, so that is checking insulation between the heater and the other pins. This one is specifically cathode to heater, and I've still got good insulation there. And then we go on to test. Now test, we then should start to see some anode current coming up, which it is. Just got to wait for it to settle a bit. So they're expecting 54.5 milliamps. We've just got to leave that for a moment or two. You can see, just while I'm doing it, you can see, look, if I put more grid volts on, current goes down. Put less grid volts, current goes up. So put it back to 9, and that seems to be settling out around about 50 milliamps by the look of it, which is about right. That's fine. Right, if we want to test the GM then, well, the way to do that is, it may need to settle a bit more, but we'll have a go. First of all, you back this off, so you have to aim for 0, and you wind the sensitivity of the scale up. You can use the fine as well, and the idea is that that is supposed to sit at 0, but it is still moving a bit, so we might just need to let it stabilise. It is still moving. Yeah, I think we're going to need to leave it a bit longer. Well, we only want to get a rough idea anyway. Just there you go. Right, milliamps per volt. It's in the good region, and then it's almost spot on. Look, there's the mark, and it's 9.5. So GM is 9.5. And then that's about it really. You can just go to the gas test. That doesn't make any difference. That's perfect insulation. Yeah, that's a perfect valve. So I've got no problems with that. I've tested the others in a similar way. I'm not going to go through all that now. It'll be very boring. Right, well that's back together now. That was quite a challenge actually, getting the Waveband selector back in. Let's move that so you can see it there. When it was originally built, what they'd done is they connected all the wires onto the Waveband selector block here, and then soldered them on afterwards. So unfortunately, some of the wires I couldn't get at, even with this removed, because there's some coils on here, and I'd have to start taking the coils off to get it on. So the few of them that I've joined, I have no idea if you can see this, but you'll see some joins in there. I think about 3 or 4 of them I've joined, and then I've replaced the wires. It was quite difficult to get at, but there we go. You know, it is back together now, and it's not looking too bad. Just whiz it round for you there so you can see it. There we go. So that's that. You know, I was thinking that I should proceed with caution with this thing, and I was thinking, I know what I'll do. I'll put the rectifier valve in first and see if I get some HT, but of course that will not work, will it? Because all the valve heaters are in series, so I have to put all the valves in, and I have to use a lamp limiter, and we just have to proceed with caution, and that's it. However, one other thing, very important thing, is the output transformer. Can you see on it? Look, it's one of those horrible old waxy capacitors, so I've got to change that first. So we'll do that, we'll pop the valves back in, and then we'll see what happens. Right, well, we've just got to keep our fingers crossed now. Let's see what happens. I've got it switched to medium wave. I'm going to turn the volume full up, got my lamp limiter in, and I'm monitoring HT there. So I'm just watching the bulb, make sure it doesn't glow bright or anything. Nothing nasty is happening. HT hasn't started to come up yet. I'm not there yet. No smoke, that's good. HT, oh, here comes HT. $70, 80, 100 odd volts. I can hear something anyway. Oh, that's good.
Swimsuits.
Oh.
No, I hadn't thought that either, but that is clearly what Sam Wolf thought. So they bring the thing.
That's good. I'm getting a lot of mains hum, but I do down here, and I've got the isolation transformer in as well, which is radiating. Let's carry on. Oh, that's really good. Yeah.
By Charles Band, as if Charles Band ever had the original.
I'm pleased with that as a start. I have already aligned it, but I will do that again. I think it's got to be worth doing. Although I don't think anything I've done should change anything, but let's realign it again. I've seen that in a previous video that I've done. I've realigned this radio. Anyway, that's what we'll do. That's a good start. I've made up my mind that I wasn't going to show you this bit because it's in one of my other videos, and if I've got my act together it'll appear on the screen now, the link. But if not, it's called Align or Not to Align, where you see I've got this rig and this is what I've built, which is as specified in the service sheet there. Before, in the other video, before I'd done any work on this, or after I'd aligned it but hadn't changed these R's and the C's, I put 20 volts in from my signal generator. I've got a 1K resistor in series, and with that I could get 1.5 volts out across the speaker at that frequency, and that was about it. And I thought, well, that's okay. And it would seem to be pretty consistent no matter what frequency I used. And at the moment I'm on 600 kilohertz, but it doesn't seem to make much difference what I use. But I'm getting much more than that, and it's going way above it now. I'm not even sure what the power rating of my resistors are, so I'm gonna take it steady. But what I want to do now is to reduce the output from a signal generator and keep that at 1.5 volts and just see how much more gain I've got. I'll just put that on speaker so you can hear it, but it's right. I'm going to go back on dummy load because it's painful. It's really loud. So there's 1.5 volts. So I've got my signal. You probably can't see my signal generator. It's 20 volts peak to peak. And I'm just going to reduce it now. I'm on 14, and I'm not even at full volume yet. So I'm now down to 8. I'm going to carry on. I'm just increasing the volume as I go to try and get that on 3. 1.4, let's get that up to about 1.5. 1.1, and it's still more than that. 0.9, 0.8, still not on maximum volume yet. 0.5, now that's 0.3, and it's still 0.3, so it's somewhere about, I can change resolution, 0.2. 0.24 volts. It was 1.5 volts on the digital one there, so let's do that. There you go. So that is 0.28 volts, and before I had to have 20 volts. So you know, that is quite an improvement. Now, in fairness, it's not all signal. Some of it will be noise, but there is a massive improvement. It's not the same radio anymore. Well, there it is back together. It's certainly got more grunt. I mean, it does sound better. There's still quite a lot of noise though, and I think that is just a weak signal. So that's the best station on medium wave.
On universal credit in the autumn statement. And
that's long wave. So yeah, I am pleased with it. It's certainly a lot better. I was hoping that the noise level might be a little bit better, but there it is. You know, I think that's what it is. So I'm very pleased with that. I think changing the R's and C's has made a big difference. It's well worth doing. So I think I think, you know, with radio like this, it's worth changing the R's and C's, worth doing alignment in that order, and it's a big improvement. It's not very difficult to do. It was quite time consuming, but not actually very difficult. Earlier on, when we were talking about electrolytic caps, I was telling you about we need to measure leakage current, and I just came up with this really simple box to be able to do that. And I also said there's another little switch and a couple of sockets on there where you put a resistor, and I said I'll tell you about that later. I'll tell you what that's all about. What it's all about is I can measure the value of capacitance with that, and not only that, I can do it quite accurately as well. Here's a little bit of video just to remind you what I was on about. A little bit. And then I just measure the current through the capacitor. It's as simple as that. I'll explain what this switch and all is about later on. Well, I've got a new 33 mic 400 volt cap, so let's just try out its leakage current. I've just charged up to 250 volts because that's about all I can get really from this rig. I could get a bit more, but 250 volts. And remember before, there was this little formula which I just got from a data sheet which says 0.06 CV plus 10 microamps should be maximum leakage current. If you work that out for 250 volts and 33 mic, it's about half a milliamp. And I've got something like about 30 microamps, so clearly that's a good capacitor. Right, so let's try and work out its value now. So the way I'm going to try and measure its value is it's all based on the fact, I'm going to say this a few times because it's quite complicated, it's all based on the fact that if you have a capacitor which is charged up, you discharge it with a resistor. If you make the product of C and R equal to 13, and the units will be seconds, 13 seconds, then it will discharge from its initial value to 10% of its value in about 30 seconds. It's 29.3 as it turns out. Alright, so I'm saying that if you've got a time constant of 13 seconds, let's say you've got the capacitor charged up to 100 volts, if you discharge it with that resistor, it will then go down to 10 volts in 29.3 seconds, 30 seconds. And to make it easier, what I've done is I've got a little spreadsheet here which should just help us. So I'm just going to do a little bit of rewiring here, and we'll go through this spreadsheet, and you can download this spreadsheet and it will come up and tell you what the value of that cap is. Apologies for my head's going to get in the way of this, I know it does sometimes. Right, first things first then. So what you do, you take the spreadsheet and you say it's a 33 mic cap, or that's what it's marked as, and what you're trying to get to is 394k to discharge it with. Now that includes your meter resistance. Now this is where, if you've got one of these old analog meters, you are better off really, because you need to sort of read at a particular time, whereas a digital one will just update, you know, half a second or a second or something. You can watch it with one of these. That's one reason. The second thing is you need to know what the input resistance of the meter is. Now these old AVOs are 20,000 ohms per volt, so if I'm going to have this on the 250 volt range, we know, let's put that right, 250 volt, we know that is going to be 5 megs. So next thing you do is you put in 5 megs in here, 5 megs. And it's suggesting a resistor of 428k. Now the important thing is that it really doesn't matter very much what this resistor is. You've got to know what it is, but it doesn't actually matter. So I'm going to just select the next one up. So I'm going to go for 470k. So I'll put a 470k across here for the minute. Let me just make sure this is turned off. Right, so there's the 470k. Chosen value of R, I'm going to put in there 0.47 mega ohms, and it's expecting that the combination of that R and that C for my meter is 430k, but we need to measure it. And this is, again, you know, if you've got a digital one, sometimes the input resistance is a bit unknown. Quite often they're 10 megs, but we just need to measure what it is first of all. I'll just put that on there. Wrong coloured leads. Don't worry, folks. Doesn't matter. Right, let's see what we get. So 425k, right, so 0.425. Okay, right, what we have to do, we have to try and measure the time that it's going to take to get down to 10%. And the other thing to note is if you've got on these old analog meters and it's a bit out of calibration, it really doesn't matter. Because, you know, if you set it to 250 volts and it's actually reading 300, by the time you get to 10% of that, the 10% is still accurate. You know, it'll be, say, 30 volts instead of 25. So it really doesn't matter. Right, I've got to set up a stopwatch now, so bear with me. My laptop is going through a real phase of locking itself up, which is what happened. Anyway, so meter is just measuring volts across the cap now, so I'm going to just try and get that to 250. I know my head is going to get in the way, so I'll apologise for this straight away because I just can't see the meter otherwise. Right, so I've got a stopwatch set up here. Again, I'll put the link to where I downloaded this. What we're going to do is when we press the button, we're going to see how long it takes to get down to 10%. Alright, so we're set up at 250 volts. And let's see whether this works. Ready, steady, go. Here we go. I'm going to have to put my head across here in a minute. Right, 40, 30%, 20%. 15, 14, 13, 12, 11, 10. 30.69 seconds. Right, let's turn this off. So go back to the spreadsheet, 30.69, you put 30.69, and it says that's a 31.4 mic cap. Now I've got faith in that. I have got a piece of paper here somewhere. Yes, because I measured that cap on my little meter here and it came up as 29.37. I measured it on, let me just find this here. I bought this little gadget on eBay only because I've got faith in this, or I thought I had, but that is saying 26.8 mic, which actually that has really got some problems. The other argument is, well, do you actually really care what value it is? Well, when I get anomalies like that, I do like to sort it out. But you know, for radio work, perhaps it's not that important. But anyway, I thought you might be interested in that. Let's try it for a 10 mic cap here. This is a high quality polypropylene non-polarized 10 mic. So if I got a 10 mic, it says I want to aim for 1.3 megs. Well, I've got a 2.2 meg resistor there, so let's pop that in. Meter resistance suggested are, yeah, 1.75 meg. Let's put in there 2.2 megs, and it's saying I'm expecting about 1.5 megs. Where's my meter? Right, let's just get this sorted. Let's see what it says. Uh, 1.504. 1.504. Right, and all we've got to do now is just rewire it. Right, let me just do that. In fact, that's all I've got to do, I think. Let me just check. Now move this over to there. Right, let's see if we can set that to about 250 volts. So while I'm doing that, we'll go for the stopwatch, set that up again. Oh, there we go. $250, spot on. Right, ready? Here we go. 36.21. Let's pop that in there. 36.21. 10.5 mic. Now again, when I measured this before on my meter, it said 10.35 mic. On the bridge it said 10.01 mic. I do need to have a look at that bridge. There's something's going on there. But anyway, look, there is a method of, if you want a reasonably accurate method of measuring capacitors, you know, there is one. So I suppose the question is, well, can you measure all values of capacitors like this? Oh, well, in theory the answer is yes, but in practice very definitely not. Think about it. For a 10 mic cap, it was suggesting that I want a 1.3 meg resistor. Imagine what I have for a 1 mic cap. It's going to say I'm going to want 13 megs. Well, my meter resistance is 5 megs, so I'm stuffing the word go. Now, okay, if you've got a very high impedance meter, you could do it, but there are practical limitations. You know, 10 mic I would have said, maybe 5 mic you'll probably get away with. Higher values, yeah, not a problem. And I believe it to be accurate, reasonably accurate. You know, you've got, well, how long does it take you to press the button and all that kind of thing, and that's why I've gone for something like 30 seconds, because, you know, however long that takes is a small fraction of 30 seconds. So I believe it to be reasonably accurate. So there we go. Let me know what you think. See whether you think that's useful or not.